Okay, so good afternoon, everyone. Welcome to the third lecture in our Introduction to Julia series. We still have Dr. Henri Laurie with us, and I don't need to introduce him any further. So thank you very much for joining us in times of load shedding, but we will post the recording of the video online later so that people that can't join us because of that will have the opportunity to watch it later. Henri, please, over to you.
Okay, hello everybody. And so what I'm trying to talk about now is a number of issues around differentialequations.jl. What I want to do is, there's a major project in Julia differential equations, and I can actually not do much better than actually look at the home page. So let me immediately share that. As you see, this is a very detailed and ambitious project. The number of types of the purpose of this package is to supply efficient Julia implementation for solvers of various differential equations. But that is actually not just differential equations, but very much related to differential equations. So we've got 1, 2, 3, 4 symplectic and stochastic differential algebraic equations, and neutral and retarded algebraic delay equations, and so on. Jump diffusions and partial stochastic partial DEs. And so it's a very, very large and ambitious project. It includes GPU acceleration, automated sparsity detection, and a number of other things. So I want to tell a little bit the story of this, how this was developed, and what is the role of the special features of the Julia language in what I think is an extremely successful project. I've briefly mentioned also, although this is differentialequations.jl I'm talking about, and the page we saw was the differentialequations.jl page. It is actually part of a project. It sits in sciml.ai, and I'll have to talk a little bit about how come differentialequations.jl went into sciml.ai. So of this enormous amount, I can present only a little. So what I want to do is to do a demo. So I'm going to try and solve one equation and 2 variations on that equation. I'll do an iJulia notebook, show that to you. And then that should give some kind of concrete idea of how this whole ecosystem of methods and types and so on actually work. So having set the scene, I will talk very briefly about what was done to create this and how it was done, and then try and set it in a larger context and close. I've got perhaps too many pages and too much of a demo, so I'm not quite sure at what point I'm going to have to really start rushing. But let's see. Okay, so now let me go and share the notebook. This is very typical of a Julia session. The notebook is not essential, but it is essential to load the packages, and I've already done so. So it's even if I reissue the command, it's very quick to do. So when you have a system that you want to solve in using different equations, all you do is you define the problem, which I do here in this one small block of code. You solve it, which is maybe 1 line, and then you plot it, which is maybe 1 more line. Okay, so I'm going to look at the Rosenzweig-MacArthur equations for X is prey, Y is predator. I was thinking about about plant herbivore dynamics, and so that's why I'm using the terms grass and buck for the dependent variables. So you just give the equations. Here's the right-hand side. And because it's in place, we give du as an explicit variable in the argument. And then we update it. So it's a vector, we can update it, and that makes it in place. But I haven't really got time to go into what all that does for you. Then, of course, you've got to give the values to your parameters. You've got to specify your initial value and the time span of your solution. And then you define the problem. So now you create a value of type ODE problem. So before we go on to solve it, I just want to briefly talk about what it means. So here, ODE problem is a type. So it's a type in the Julia system of types. It's immediately when you create it, you situate it in that system of types. And actually, there's an abstract problem that ODE problem is a subtype of this particular type. And I'm going to just paste it here. And then we can see that there are 5 types of problems, 5 problem types under abstract ODE problem. Abstract ODE problem is a subtype of another further abstract type, and it has more abstract types. And in total, there's something like 17 problem types, not concrete, well, leaf types are not concrete, and I'll have to explain what that means in a little while. Okay, so I can't go into all of that. There's this quite good help if you ask for it. It's fairly detailed. I will briefly show what it looks like. You get all of these things about mathematical specification, some details, problem types. So the Julia type, Julia help tends to be perhaps a little verbose, without really people who want a very short, quick guide to syntax or something are usually can be a little bit frustrated. Okay, so having defined the problem, we simply solve it. So we call the solver with just with all the default values, and if we do that, why is it now slow? So I thought I had run all of these beforehand, but now I see that it wants to be slow. I'm not quite sure why. Anyway, it says success, which is a bit of a surprise, because I was assuming that it was going to be an error, but it isn't. So let me just briefly explain that here's an option with a much finer tolerance than the actual default. And you can actually, so that it's very easy to give these keyword values, their default values that it runs with. It's 10 to the minus 6, I think, 10 to the minus 5 most of the time. So the syntax and running this is very simple. And then we can just plot it. And now I'm going to have to replot these as well. So so this this plotting works. This plot command is actually, my word, this is not a solution. What did I do wrong? I don't know what I changed, but it's not coming out what I expected. This plot command here is from the plots package. It's not actually code that is defined by differential equations. So this is differential equations has various types, and these types are then plotted. They pass to the data that is packaged in those types are passed to the plot command of the plots package, and using a plot recipe, it then puts out the plots, and we get that. So this is what the phase plots might look like. You can see that there's a little bit of complexity in the phase plot. I think I know what happened. I didn't actually rerun that. I needed to rerun that. And then I can just rerun all these things. And then you can see that now, if I have it without the fine tolerance, then it integrates for a while, but then you get these very large negative values. So it becomes unstable, numerically unstable. To cope with that, you can just give the much finer tolerance. Yeah. We'll see later on why we got this shape, and then we had that shape. Okay, so we can modify this to a system which is non-autonomous. The previous equation was not time dependent. Here, the W depends on time, because this bit of code decides whether T is in the first or the second half of the year. And if it is, then W is 2, and if it is not, then W is 0. That is the ternary operator in Julia. I think it occurs also in some other languages. And so all we need is to put in to change the parameters a bit so that there's an extra parameter, and to put in this line of code here, and to put the W there, and then everything can proceed as before. And the solution is very fast. And we see that now the solution is not satisfactory because there's this peculiarity here. That's obviously a numerical artifact, and we'd like to remove it. And what we might try and again to set the accuracy much lower, but Julia has a pullback mechanism, which allows us to implement every time this is true, every time that the remainder of division by half the year is 0, we change the value of the first element of the parameter vector, which is this value of W here. So now again, we've changed the parameter vector, and we've put a value of W at the start. And we now just change the value of W every 6 units of time. In order to do that, we have to construct a callback, and particularly we use this type constructor. So now we have CB is a callback, and we can pass it to this keyword here when we define the problem, and then it runs pretty quickly. And if we do that, we get a much, much nicer plot. Alternatively, we can, instead of extending the problem, making it non-autonomous, we can extend the problem by putting in some different delays. And I wrote the equations here just to make it clear to you absolutely that the delay affects only the actual dynamics of the prey population in absence of predators. So this is what the prey population is doing within itself. Its growth rate, dx by dt, depends on x some earlier time. This is done in population dynamics to look at maybe the effect of a maturation period before an animal can start reproducing. Now you have a different problem. You're going to define a DDE problem, and it's going to need a value for the keyword constant lags and a value for the function there, which is the history function, and which is defined here. So this can be this says that the history is just constant before in the lead up. So you have to, when you have a differential delay equation, the initial value by itself is not enough. You have to just give an initial value over an entire interval as long as the delay. So this is just says it's constant. Here I've made a delay which is relatively large compared to the a typical period as we saw before. And it has to be implemented in a way similar to this. So you evaluate some value for x at t minus tau, and you put it in there. This one here means it's only for x and not for y. And so then you can again, so it's a very simple interface. The difference is just one extra variable in the argument, or more precisely value, and then we have defined it. And now we run this, and it takes a little longer now, but we can see that with a t-tau of 1.2, the shape of the period is slightly different, and we've seen this shape before. And the reason I had it before was that I've used the same name. I didn't use a different name, and so it was using this function to in the previous one. So what I just want to emphasize, it was very simple to change the existing code into something different. It was very simple to interface with the plots package to produce plots. So let me stop that share, start the other share. Okay. That was the demo. And there were just 3 steps. Each step is only a few lines of code, and it's the crucial dependence on having problem types. That's why everything can be done in this very unified way. The user code is then instantiates the given type. There are compilation times, as we saw, but otherwise the solutions are extremely efficient. And that crucially depends on multiple dispatch and specialized compilation. So I'm emphasizing these things because they are features of the Julia language that I think in many ways are quite difficult to reproduce in other languages. And now you can actually explore into related problems very simply. You can compose different extensions. So we could, if we like, in the situation of the DDE, we could have a DDE and a seasonal problem together and see how that worked. Obviously, that's computationally very challenging, but that could be done. Okay, so what you've just seen are the interfaces in action. I mentioned this because there was a complaint about Julia that it doesn't specify how to do interfaces, but this clearly is interfaces and a very unified interface for a very wide range of DE-related problems. It depends crucially on there being problem types, and that these problem types are in a hierarchy, an abstraction hierarchy where they can be related so that type inference can be done. Because the solver dispatches on problem type, you get the solution types and the plot recipes dispatched on the solution type. So these are interfaces, these types, the problem types and the solution types allow the dispatch of a wide variety of methods depending on problem or solution type. And so this defines a very clear set of interfaces, which is the core structure of DifferentialEquations.jl. Okay, so that is gives you an idea of what is happening in DifferentialEquations.jl. And so the people who made it, what did they actually do? Well, in January 2016, there was only one person involved, and that was Chris Rakauskas. He was doing a PhD. But he went on to GitHub and he started making a couple of packages and invited participation. They very soon had the DifferentialEquations.jl meta package, and by November, they had so many repositories and so on that they felt they needed to make a GitHub organization. So this is in less than a year. And by March 2022, they renamed the Julia DiffyQ organization to mark the fact that they were going beyond just DE related software, because they were turning to integrated modeling that combined data and analytical models and machine learning, and a very big jump in the number of repositories. Okay, so all this code, what did it actually comprise? Well, a very large set of problem types, a whole type tree. And the point to note about that is that this type tree has leaf types that are not themselves yet concrete types. They're merely parameterized. And so they need to be given values for those parameters before they are instantiated. I want to give you an example of the kind of thing, a much simpler example. If you have an object of type vector and an object, a vector by itself cannot be a Julia object because it's not a concrete type. It's not an abstract type either because it doesn't sit anywhere in the Julia type tree. However, if you specify that all the elements of your vector are of type float64, then it becomes a concrete type. It doesn't have to be a primitive type. You could say a vector of type any would still be a concrete type. So that's what you have to do with all these problem types. You have to give them parameters. And we saw that the ODE problem that I defined in the notebook had the parameter was that its dependent variable was a vector of type float64 and its independent variable was a scalar of type float64. And having got these very many types, they then implemented very, very many methods. However, there is only one generic function, solve. So every time you want to solve something in differential equation, you call solve. And depending on the type that you supply, solve then specializes to particular things. And if you've made sure that you have type compatible functions and it's type compatible with your initial value and with your dependent variable, then they will be statically compiled and they will be very fast. It really does compete very well. So in terms of what they were doing, having done all that, it's also crucial that they just kept expanding their ambition. So initially, there was a single PhD. Admittedly, it was something as ambitious as the algorithm and code for an adaptive Runge-Kutta method on a system of stochastic PDEs. These are just heat equations, so not the most difficult PDE, but still. There was spatial issues and so on. So it is really not a simple problem. I'm not quite sure why ODEs came into it particularly. Of course, Runge kata tends to be for ODEs, and so maybe there was some kind of discretization that turned the stochastic PDEs into systems of ODEs. But they provided a unified testing and comparison so that it could compare all the known methods and could also compare it with other software packages. There's a very remarkable set of comparisons that they've done in which Julia does extremely well. I had wanted to include it, but I think it takes too much time to explain it, and just haven't got quite enough time for it. So what then happens, first it's all known methods for ODEs only. Then it's a uniform interface for all DE related problems and for the methods for solving them. So they really go a long way into, you know, when I was starting to learn about numerical methods for ODEs, that was in the 90s, it was quite clear that everything was, there was a whole set of different areas where there were specialists in the numerical methods for different areas, and there was no sense that they could all be unified. So it was always, it's been astonishing to me that there's a uniform interface for all DE related problems, and that many ideas from one area can now very simply be applied in another. Having got that, they went on to saying, well, it's actually artificial that we separate the process of gathering data and the statistics of the data and all that from the process of solving equations, not merely formulating, but solving them. And that machine learning gives us a way of doing this for very large amounts of data. So that's where SciML comes in. Okay, so now, if they've done all that, how did they actually do it? How is it possible that starting in 2016, they have this incredibly large and ambitious system going? In fact, they had most of it going by 2018. So it starts as a single PhD, Chris Rukakis, and I think one should not underestimate the importance of this person, because he actually was able to have the vision of the entire project, to drive it, to get people involved, and to make this whole big thing. It's quite unbelievable that one person can do it, but as he himself says, it depends crucially on Julia as a language. So his project was on the hindbrain of zebrafish, the development in the embryo, and the particular idea that he and his supervisor wanted to understand was that the variations in the noise, so it's a chemical system, there's always noise, are themselves important, not merely the signal, but actually the variations. And they wanted to get some understanding of that. And that led to a multi-scale model, which had lots of stochastic PhDs that modeled gene regulation, ontogenesis, spatial noise, inside cells, between cells, in the whole large-scale system. They would then want to, because it's stochastic, they want to do many runs and see like things come out of comparison. But each particular run would occasionally have very rapid shifts between, there'd be a relatively low level of noise at one particular level, then there'd be a shift to another level, a sharp shift, and then a relatively low level of noise there. And so this was this, what he calls the pathwise stiffness. So every now and then there'd be this big shift, very large eigenvalues in the Jacobian, stiff for a moment, and then, but on that particular path, on another path, that stiffness would happen at another time. And so the MATLAB just took hours, and that was really the motivation for going to Julia. It's hard to disentangle DifferentialEquations.jl from Rukakis's PhD. I think going by a Reddit post from September 2017, that he basically were running them almost in parallel from a very early stage. But I haven't really been able to get the very detailed timelines. So in order to go just beyond what Chris Rackauckas did, I think it's really important to note that he had a vision that he was able to impart to other people, and that led to their participation. So this vision of his in the early stages was maybe just his own project, which was already quite a big thing, but he rapidly expanded, and they brought in Google Summer of Code participants. So basically it was all volunteer. They weren't able to fund a lot of participants in this project. But Google Summer of Code, of course, will pay for students to write code. And the Julia context made it possible for people at a relatively low level of expertise of a typical Google Summer of Code participant to come up to speed and write cutting edge numerical software as a Google Summer of Code project. It also, when in terms of expanding beyond this PhD, the plots project package, the linear algebra package, the static arrays, there are very, very many others. And there is the interaction with the Julia language itself, the core developers of the Julia language. All of this actually was very important in getting this to go beyond one PhD project. So unfortunately, the timeline I'm going to give is quite rough, because there's no system of release notes or roadmaps. In TimeL.ai news, you can get something about many of the main releases, but not all. And there are also some blog posts and so on. But what I've got is just to have the main things, that version 1, which was released in 2017, in the middle of 2017. In that time, Chris Rackauckas teaches himself Julia. He replaces MATLAB in his PhD, and makes the Julia code public and gets quite a lot of participation. And then the participation, the Google Summer of Codes, they managed to get, by the end of version 2, to get all ODE related problems and methods to in under one package. It's not uniform. The uniform interface only comes along in version 4, and the expansion into more PDEs than what Chris Rackauckas did in his PhD is quite slow. It focuses on stochastic differential equations and on ODEs and the callback interface and that sort of thing. But those stuff, it's still happening, it's still coming along. And then version 6 in 2019 or so, the machine learning, which then becomes the main focus of SciML. I think Chris Rackauckas still dominates the commits on GitHub, and he wrote a very large part of the codes. It's all under his name. Whether he wrote all the code or merely did the commits, I cannot tell. But it's a fantastically large amount of stuff. And I think that emphasizes the role of lucky chance. So there was at the right place in cyberspace was Chris Rackauckas, who was not a computer scientist nor a programmer. He sees himself as a mathematician, applied mathematician, I guess. He can code. When he starts out, he's obviously fairly good at coding in a variety of languages, although he doesn't see himself as a programmer at all. And he wants something that existing languages cannot give him, but Julia can. Part of his PhD is a very, very long run on a supercomputer available to him at UC Irvine. But in the context of the rest of his project, the amount of work done in Julia is probably similar to, well, how can I put this? If he had done his entire project in the context of that supercomputer, he would not have gotten very far. That's my belief. That in that sense, Julia gave him what these other languages could not. He's incredibly productive. He works very efficiently, and he works hard and long hours. So it's an unusually strong combination. And what is also important is that when he starts, which is at the end of 2015, the beginning of 2016, the Julia language is mature enough to give it credibility. So if somebody, an ambitious PhD student says, I want to use Julia by late 2015, that's a credible choice. But at the same time, the Julia language is young enough and small enough that the main Julia developers work directly with Crystal Karkas and quite vigorously and in quite a number of issues. If he sends an issue to the main to the GitHub of the main Julia language, it gets a response, it gets fixed quite quickly. And of course, he's got all these collaborators. He responds very effectively and very quickly. In my own experience, amazingly fast. I mean, I've only asked for a few things from him, and they just came. So I think that it's a little bit of an accident that someone like that comes along at that juncture of opportunities. But of course, this kind of accident is at the heart of these the rapid technological developments in many cases. Okay, so now you've got the SciML software ecosystem, which is a very grand plan. We have a little bit of time, so I think I will just try and go there. Yeah. Okay, so this is the SciML open source for machine learning, a unified composable open source for scientific machine learning with differentiable programming. So what they've developed is a method of automatic differentiation, which will differentiate any program, truly. It's an extraordinary idea, but they will do it. It's modular, so things can be combined to make different things, just using bits of modules, and it's highly performant. There's the physics-informed model discovery. There's it's not Julia exclusively, so diffie-Q-Pi, diffie-Q-R, so bridging with Python and R. Where's modeling toolkit? So you can actually it's a rewrite way of modeling toolkit is, I think, more ambitious than simply rearranging equations for better stability. But it wants to kind of unify also a lot of things that weren't apparently unifiable before. There's neural PDE, differentiable data structures. And so it's actually an enormously large and ambitious project for essentially a whole new style of doing modeling. So I'm in two minds as to whether such an ambitious project is really going to succeed, whether there are going to be that many people who start doing things really the SciML way, but it's very interesting, the ideas that are being put together. And I think a lot of people might well be inspired by it without necessarily adopting SciML as the way that they do the work they want to do. Yeah, so this idea that you integrate the data and the modeling, and that you use machine learning to cope with a huge amount of information, that can be done anywhere in the modeling pipeline between data and machine learning. So this is the plan, and there's been a lot of success. It's by no means just hype. But how easy it would be for other people to use it, and how popular such a thing would be, I think that's definitely, I'm going to wait and see, but who knows. Okay, so this, just to summarize, I hope I showed you that, like Julia itself, DifferentialEquations.jl is easy. It's very easy and quick to use. It's very fast, and except for a bit of compile time payment. It's very generic. It's very composable, and it's also very ambitious. So all of that is very profoundly enabled by the Julia language itself. In particular, the combination of the type system and the multiple dispatch and the late compilation. All of the late compilation allows highly specialized compilation, essentially static compilation, so very fast, very performant code. And the other two means that you can extend a two-dimensional extension. You can extend your data structures, you can extend your methods in a very coherent and consistent way, where there don't appear to be any hard boundaries in this sort of abstract two-dimensional space I'm thinking about, where you can't move with more data structures, more methods, and combine them more and more ways. And so every time that I saw how ambitious the people in Julia and basically Chris Rukakis, under the leadership of Chris Rukakis, how ambitious they were, I thought, but this is over ambitious. This can't work. And every time they delivered it in half the time that I thought would be vaguely possible. I've been incredibly impressed. Okay, so having said that, I have a short session, a long session, I find I have a relatively short one. So I've really rushed. I've still got the demo open, so I can take questions on that. I just want to look briefly towards next week, where I'm going to ask whether these aspects, that you can do your entire project in one language, that there is massive code reuse, not across the whole of the Julia community, and that development itself, the writing of code, the going from ideas into designs into code is very, very fast. Is that actually relevant to high performance computing? And with that, I say thank you very much.
Sorry, Henri, thank you very much. It was again a very exciting lecture, and I'm really curious. Oh, sorry, what happened to my? Here we go. I'm really keen to try it out.